So one of the things that we are learning this week is about functions. And one of the most important things to know about functions is function notation, how to use it, what does it mean. And this is actually one of the biggest places where I see people make mistakes. So hopefully this will help clarify things for you. So first off, what is a function? A function is a relationship between you have inputs and outputs, where for every input there's only one output. So an example in real life, like there are functions that don't have to be numerical, it doesn't have to be an equation, but let's take your grades. You earn a percent, like say you have a 65% in the course, and there's only, that would be your input, and then the output would be the letter grade that's associated with that. So 65% is considered a D. So you have only one letter grade that goes with each percentage. That is a function. Basically, if you give it the inputs, you know what the output is. There's not multiple choices. There's only one possible answer to that question. I have here a visual example of a function with just numbers, where if you're looking at it in math terms, you've got your input, which is x, and your output, which is y. And so your input numbers, your x, gets associated with a specific y. Think of these as ordered pairs. So every x has one y value with it. And that is what makes it a function. If you have an input in x that has multiple y values, that means it has more than one output, and it is no longer a function. So function is specific where each input has only one possible output that is associated with it. So if we have equations that are functions, then we use special notation to indicate that, so that you know specifically this is a function. For every number I plug in, there's only one output number. So we use this, and this is pronounced f of x right here. We replace a y with that. That is considered a, it's a notation, it's like a single symbol. It's sort of combined together. So if you had an equation y equals 2x plus 5, instead of writing y, you'd write f of x equals 2x plus 5. And this is indicating to you that this particular equation is a function. So this f of x, what that means, that symbolism means, is the letter f is the name of the function. So you don't have to use f. You could use any letter of the alphabet. It's just the name you're giving to the function. What's in parentheses, the x, that is telling you what your input value is. So if you had a different input, if it wasn't x, but your input was t, then you would have t inside the parentheses. I already mentioned you read it out loud as f of x. And the key thing is that this is not multiplication here, because this f of x is like a single symbol. It doesn't get split apart. It's one block of symbol here. It's not multiplication of two variables. It's very different. It's very specific notation. So you are not going to be solving for f by dividing by x or anything like that. This f of x stays together. It doesn't get split apart. So there are actually lots of benefits to using this notation, which is why it exists. So first off, if you have lots of equations and if they all used y, it could get really confusing. So by using function notation, you can give a name to each equation so you can keep them apart. So some common examples are, instead of y equals, you'd use c of x. So that represents cost. You'd use c for cost. You can then use r of x to represent your revenue, and p of x equals profit. So in business, you often have equations for cost, equations for revenue, equations for profit, and instead of just all having them y, which could get really confusing, you can name them c, r, and p, so you can keep them apart, and you can keep track of them. So that's one of the benefits of using this notation. The second benefit is that it tells you what the inputs and outputs are. So if you see this is still function notation right here. It's just instead of x, we have a number, but this would be c of 2 equals 5. This is telling you c is representing cost. your input is 2, so let's say you have the cost to produce 2 units, and then 5 is the output, so that would be like $5 or whatever your units are. So this notation tells you what your input was and your output, which gives you more information than if you just saw the equation y equals 5. You might be like, okay, that's $5, but what's $5? But if you see C of 2 equals 5, it tells you, oh, the cost at 2 units is $5. You get a lot more information with that notation. The third benefit is that it actually gives you ordered pairs in the notation. So again, we're looking at this notation, C of 2 equals 5. This is just an example. And this gives you the ordered pair where your x is 2, because that's what's in parentheses, is your input. And the output is what it's equal to. So you have an ordered pair 2, 5. So if we were using y, which we have been using, and you just got y equals 5, you don't know from that equation what your x was. But if you use C of 2 equals 5, you know both the x and the y. And so you have more information. And then the last reason why function notation is very helpful is it allows you to do, say, you have to do some unit conversions, or you need to plug in a different variable. Sometimes you plug a function into another function. So let's say this equation, this hypothetical equation I've been using, C of x for cost, is giving you in dollars, but you actually want to measure it in how many $1,000, or if you want to have it in thousands, then you can instead plug in x divided by 1,000, where let's say your C of, I don't know, 2,000 equaled 5,000, would be $5,000. Now let me actually write this down. So an example of this would be, oops, trying to find the pen. So if we had a C of 2,000, saying 2,000 units was equal to $5,000, the cost. If you wanted to convert it so that you're measuring in $1,000 instead of dollars, if you divided your input by 1,000, so that it would be 2,000 divided by 1,000, you're basically dividing your x by 2, then your output would be 5, and then the units would be $1,000 instead of $5,000. So you can use function notation to do unit conversions. Another example would be the distance formula. We have d equals rt. You can write that as a function, and you could have your equation for distance in terms of miles, but then let's say you want to convert it to kilometers instead. With function notation, you can plug in for x, instead of x, plug in something else that will do the unit conversion for you. So function notation has many benefits, and so from this point forward, we're going to be using function notation for the most part instead of just using x and y. So instead of y, we'll be using things like f of x or g of x, just because it does give us more information, and so has a lot more benefits than just using y. So it's really important to understand the function notation because it's going to be used for the rest of the class. So when we're actually using this function notation, there are basically two mathematical things we do with it. The first is to find function values, and this is also called evaluating. So you might be told to evaluate a function. And what that means is you plug in a number for x, and then you simplify only the right side using the order of operations. So the general rule with function notation is if you're plugging in numbers, you only touch the right side of the equation. You never really touch the left after you've plugged in the number. The second thing you can do with function notation is solve. So you might be told to find the zeros of a function. And so what you do is you first replace your function notation with y. So instead of writing f of x, you'll write y. And then you might be solving for x, or you might be plugging in numbers for y or something like that. So those are the two things that you do with function notation. And generally, you end up with function notation solving for x in some form. You just be replacing the f of x with something else. So what I'm going to be focusing on for all of my examples is going to be the evaluating portion of function values, because that is the basic thing that you want to really understand how that works. And then you'll be doing solving like next week, and as we go further into the rest of the second half of the class, basically, then you'll start getting into more of the solving kind of things you do with this. But for now, we're just going to focus on evaluating, which means we're going to be plugging in numbers for x and then following the order of operations. But we also need to understand function notation as well, so we're going to do some things other than that as well to kind of get you used to it. So here's our first example. Evaluate f of x. So remember that instead of y, we are writing f of x. So these are the same things. So this is the same as y equals. So we have f of x equals x squared plus 3x for the following given values. So they're giving us an equation, and we want to find, this is f of -2 and f of 1. So the function notation, what is in parentheses is your input value. So if we see f of -2, this is telling us that our input is -2. So you're going to plug -2 into your equation. So instead of, if I have f of x, this is going to tell me that x is equal to -2, because I have basically taken what was x right here, and I am replacing it with -2. So everywhere you see x, you're going to plug in -2. And this is what we're going to do when we evaluate. So step 1, I can get to the right thing. Step 1 is to plug in for x. So we have f of x. We're now going to have f of -2, because instead of x, we're replacing with -2. And then we also do that on the right side. So we have -2 squared. So I have to put the -2 in parentheses because I'm squaring the whole thing, not just the 2. I'm squaring the -2. And then we've got plus 3x, and that's going to be plus 3 times -2. So everywhere I see x, I've now replaced it with -2. And then your second step is to simplify the right side. So we follow the order of operations on the right. We do not touch the left ever again. You don't do anything else on that left side. We now only touch the right side. And so what helps to remember that is maybe to not even write down anything on the left side. Is just to make something equal. Like, because I have words here, I'll start with rewriting my f of -2 and then start doing the order of operations. But it helps to maybe then each step just keep doing equals and not do the left side. So order of operations, the exponent comes before multiplication, but we can do those in the same step because they're separated by a plus. So -2 squared is 4, and then I have my plus, and then 3 times -2 is -6. And then we add 4 plus -6, and that gives us -2. So our answer, the way we write our answer is f of -2 equals -2. You do not divide both sides by -2 to solve for f. We're not solving. So the word solve means you do things on both sides of the equation. There is no word solve here. So we are not doing things on both sides. Evaluate means you do things on one side. So we're only doing things on the right side here. There is no dividing of both sides because we're not solving. It's really important to understand the difference between solve and evaluate, because you'll get different answers depending on what you're asked to do. We're told to evaluate, So we are only doing stuff on the right side after we plug in our numbers. We do not touch the left side at all. Are there any questions on this first example and that difference? Okay, so let's take a look at this second one here. We have f of 1. So what's in parentheses is our input value. So we are plugging in 1. So this is telling us that x is equal to 1 because we have 1 in the parentheses. So I need to replace everywhere I see with x with the number 1 in my equation that we're given. So we have f of 1 equals 1 squared plus 3 times 1. So following the order of operations on only the right side, 1 squared is 1, 3 times 1 is 3. You add those together, our answer is 4. And we write our answer as f of 1 equals 4. So no dividing going on here. We're only plugging numbers into the right side and then following the order of operations. Are there any questions on these two examples? Okay. This one is a tricky one. And so it's not, I shouldn't say it's tricky. I guess it's easier than it looks. Maybe I should say that. But you do have to kind of think here. So it says to evaluate h of x. So I used h in this case. So you can use different letters, but it's still in function notation. So if you see a letter, parentheses, another letter, that is telling you it's function notation. So this is specifically, it's in function notation. We have h of x equals 5. And we want to evaluate h of -7 and h of x plus a. So on the left, we're plugging in a number for x. On the right, we're plugging in x plus a instead of x. Now looking at what we have h of x equals 5. So if I plug in, so first off, on the left, we've got h of -7. That -7 is saying that our x that we were plugging in for is -7. So we have h of x, but instead I'm going to write -7. And then on the right, I have 5. There's no x's on the right side. So there's nowhere to plug -7 in on the right. It's just literally 5. And there's no order of operations to do on the right side. It's just 5. So our answer here is just h of -7 equals 5. We've evaluated, we plugged in for x, and the output is 5. We didn't even really need to do any math. So now think about what's happening on the right side. So the example on the right, we're still using h. We're replacing x. We're now going to replace it with x plus a. So instead of writing x, we're writing x plus a in there. So on the left, I'm going to have h of x plus a. What am I going to have on the right side here? So you guys can feel free to type it in the chat. What is going to be on the right? 5. So that Ryan was really quick on that. It's going to be 5 Because that's all we have on the right side is 5. There's no x, there's nothing to plug in. It's still 5. So this is why I said it seems tricky, because it seems like you're plugging in something complicated, but it's actually simple because it's just literally 5. Because that's all you have on the right side. You don't actually have to do any math. All we're doing is changing what we're putting on the left. But it doesn't matter what we put on the left because the answer is always going to be 5. Are there any questions? Okay, so here's, let's look at this one on the left, g of 1/3. So what am I plugging in for x? What is x equal to if we have g of 1/3? So go ahead and type that in the chat. So we're looking at g of 1/3. What am I going to put in for x? What is in parentheses? So what we have in parentheses is 1/3. This is telling us that x is equal to 1/3. So you just look, what is the number in parentheses? That is x, because we're told g of x, and that's also in parentheses. So I want you guys to try to simplify this on your own. We're going to first write g of 1/3. And then that's equal to 1 over x, and x is equal to 1/3. So what would this simplify to on the right? We have 1 over 1/3. What is that equal to? You guys can type it in the chat. You can use a calculator if you're not very good with fractions, that's fine. Got an answer of 3. That is correct. So if we have 1 over 1/3, you're taking the reciprocal of 1/3, which is 3. So our answer is going to be 3. So when we write our answer here, we're evaluating. We write g of 1/3 equals 3. So we have just evaluated g of x for 1/3. And we got an output of 3. Now the example on the right, we have g of t. So now we have a different letter here. This is just saying we're going to replace the letter x with the letter t. So normally it'd be x inside the parentheses. Now we're going to make it equal to t. So we're just doing a substitution here. Everywhere you see x, you're going to write t instead. So we get g of t equals 1 over t. And that's all we're doing here. We're just changing the variable from x to t. We're still evaluating. Evaluate means basically plug in whatever is in the parentheses. So that's what we did. Everywhere we see x, we're now replacing it with the letter t. Are there any questions? Okay, so here's another one. We have a different letter, K. And this is the nice thing, is by using these different letters, you can tell we got a different equation. So we've used G, we've had H, we've had F. Instead of using Y for all of them, we're giving them different names, which tells us it's a different equation. It's really helpful if you saw these all on the same paper, then you know, okay, these are all different equations. I know which equation I'm using. So in this case, we have K. So K of X equals the square root of X plus 1. So we're going to evaluate for the following given values. So on the left, we have K of -5. So what is -5 going to replace? What in our equation for K of X is -5 replacing? X. We've got multiple people there. We're going to be replacing X with -5. So instead of K of X, it's going to be K of -5. Then I've got my square root, and then I have my X, which is -5 plus 1. So now we want to simplify on the right side. We're following the order of operations. So I need to add those values inside the square root. So -5 plus 1 is -4. We're going to get an imaginary number here because we have a negative inside the square root. So the negative gives us an I outside the square root, and then we have the square root of 4, which is 2. So we're going to write this as 2I. So we're just plugging in a value for X, following the order of operations. In this case, it actually gave us an imaginary number 2I. Now, just as a general note here, most functions should be graphable. So we usually restrict the domain. And the domain is the input values. So we usually restrict and don't plug in certain values. Restrict the domain to avoid complex answers. So functions are something that we usually graph. And we haven't done any graphing here because we're just, oh, I don't know how I zoomed in. That's interesting. There we go. So we haven't done any graphing because we're just working with the notation, but a lot of what we're going to be doing this week and following is a lot of graphing. And we can't graph complex numbers. We don't graph imaginary numbers. So in general, you would be restricting your domain so that you would not plug in numbers that would cause imaginary output. Like we would not allow us to plug in -5 because we can't graph it. But in this case, we're just practicing evaluating, and so we could get a complex number. It just would not be on the graph, and it would not be in the domain when we're looking at it graphing. But as far as what we're doing today, which is evaluating, all we care about evaluating is plugging in the number that they're telling us to plug in. And so in this case, that gave us an imaginary number. So just keep that in mind, is most of the time when we use function notation, we like to use it in terms of things we can graph. So let's look at the equation on the right. We've got K of X plus H. So sometimes it gets confusing when you're plugging in an X and you already have an X in your equation. So sometimes it's helpful to kind of make like a color for what you're replacing. You know, so instead of the letter X, wherever I have this blue here, that's what I'm replacing. So when we have K of X plus H, everywhere where I have that blue, I'm going to write x plus h. Because sometimes it can get a little confusing, but if you do it as far as colors, you can kind of see the pattern here. So everywhere we see x, or in this case the blue, we're writing x plus h because that was what was in parentheses. And then I still have that plus 1 underneath there. So if it helps you to think about, well, whatever my inputs are, you can kind of color code instead of use the X, and then you can see where you're plugging things in. And then you would go to simplify. Now on the right, we don't really have anything to simplify because there's nothing to add. X, H, and 1, they're not like terms. So all we're doing here is just changing what our variables are. We took an equation that had just one input, and now we've made it have two inputs, x and h. So that's another use of function notation, is you can take something and you may have one input, and now you can plug two things into it and get only one number out. Are there any questions? Okay, so next question, and I'm actually going to put a poll up. This is going to be yes or no, and it's going to be, do you have to take calculus? So I've just started the poll on the screen. So I just want to see how many of you are going to have to take calculus. So you should see it on your screen. It's just yes or no. I have only one response so far, which is a yes. If you are in computer science, you generally have to take Calc 1. If you are in engineering, you definitely need to take calculus. I think, I don't remember if the IT degrees require calculus. Business does not. So if you're in business, that's a no. So we've got two no's, we've got one yes. And the reason why I'm asking is because this kind of thing, okay, we've got another, so we're half and half right now. We've got two no's, two yeses, and another, okay, so we've got 3 yeses, 2 no's. So the reason why I'm asking is because this example here is often something that you have to do in calculus, where you're going to have to plug in something into function notation and simplify it. So what we're doing here is, again, we're going to be plugging in that x plus h thing. That's often used when you're doing a derivative. There's something called the limit definition of a derivative, and you're plugging in things where you're replacing x with x plus h, and then you're going to do a lot of simplifying and a lot of algebra in order to find your derivative. So for those of you that are going on to calculus, and you do have to take pre-calc first and then calculus, this is something that you're going to see. So I wanted to show you, kind of get you started on what you would be doing, because it's used for calculus. It's how you figure out derivatives. So it's actually a very important thing. So we've got f of x equals negative 4x squared minus 5x plus 2. We're going to find and simplify f of x plus h. So find means basically plug it in. Simplify means now you need to simplify the right side. So just to kind of help, I'm going to do my little color coding thing that I was doing here. So to kind of help us keep track of what we're plugging in. So we're plugging in something for x. And so we have negative 4 and then something squared minus 5 times that something plus 2. So instead of x, everywhere we see x, we're going to be replacing with something else. And that is going to be this x plus h that we're going to be plugging in. So everywhere where I have that orange, we're going to replace it with x plus h. Oops. Trying to switch between my pen and my highlighter. So I have f of x plus h. So I'm kind of color coding here. Was -4 times, and then we have x plus h squared minus 5 times x plus h plus 2. So this is the find part where it says find. Just this part where I plugged in x plus h, that is the find part of this. Find and simplify. Simplify is going to be everything that we do after this, where we're going to be trying to take this complicated thing on the right and make it smaller. And we're following the order of operations to do that, which means first we have to deal with the exponent, the x plus h squared. So we need to actually FOIL that out, x plus h squared. So what helps a lot of people is to write it twice because it's squared. So that way you can do the FOIL process on it. So just write it twice. And we're going to FOIL this out. So we're doing a lot of algebra here. So we're going to multiply the x times x, and that we still have that 4 in front. So I've got my -4, and then in parentheses, x times x is x squared, and then x times h, which is literally xh, h times x, and then h times h. So it does look kind of long here, kind of long and messy. And then we can also distribute through the parentheses here the -5 times x, so -5x, and the -5 times h. And then we have this plus 2. So this is getting kind of long, but this is part of the simplified process, is that first we have to make it bigger before we can add things together and make it smaller. So just, you may not realize this, but this x, h, and hx, these are like terms because they have the same variables and the same exponents on them. They're in the different order, but they are like terms. So those add together to get 2xh or hx, whichever you prefer to write. So we're going to have this -4 out here. Then x squared plus 2xh plus h squared minus 5x minus 5h plus 2. And now we need to multiply through the parentheses the, so what color do I'm running out of colors here. We can use purple, I guess. The -4. So we get -4x squared. And then -4 times the 2hx. So -4 times 2 is -8xh. And then -4 times h squared. And then we still have our -5x minus 5h plus 2. And then you're looking for like terms. So we've got an x squared, but nothing else is with that. We have an xh. It's the only xh we have. We have an h squared. It's the only thing we have. That's that. We have an x by itself, nothing else. H by itself, nothing else matches with that, and a 2. There are no like terms in this last step. So this is the simplified form. Even though it's actually longer than what we started with, when we say simplify, that means we do any multiplication, including FOIL. So our simplified form is f of x plus h equals negative 4x squared minus 8xh minus 4h squared minus 5x minus 5h plus 2. And this is a very, very long thing. Now, when you're doing this in calculus, when you're going to have to do something like this, you'll be subtracting from this thing a lot of stuff and things will cancel out. So you will have this really nasty looking thing when you do this in calculus, but it will simplify because you'll be subtracting things from it, you'll be dividing and things will cancel out and it will actually get a lot smaller. But this is one of the first steps that you're going to have to do when you do that definition of derivative. And so it's really important for you to see first, what does it mean when you're told to do f of x plus h? And then what does it mean when you're told to simplify it? Simplify means you need to multiply your stuff out, even if it does mean it gets more, bigger and longer. It's still considered simplified because you don't have things that are exponents, you multiplied it out. And you want to take your time on something like this because it's really easy to make a mistake. And that's why I tried to do some color coding here to make it a little bit easier to try to go backwards if you think you made a mistake somewhere, because it is really easy to mess something up, especially any signs. Are there any questions? But I can tell you something like this would not be on a quiz because this is a lot of work. So we would not be asking you to do something like this on a quiz. We'd be asking you to just plug in numbers. But this is, for those that have to go on a calculus, this is something that you're going to need to do. So that's why we're covering it. Okay, so here's a different type of function. So this is a function that is not given as an equation. It's given as a set of ordered pairs, but it's still a function because you have every ordered pair, each x in it has only one y. So this is a function. You can have functions that are a list of ordered pairs and are not equations. And you're still asked to find certain function values. This is another thing that if you're told to evaluate something, it's also known as find function values. So let's put a little note here. Find function value means find the output. So that means find the y value, basically. So if you're told to find the function value, you're looking for the output. So on the left, we have determine f of 9. So this 9, x is equal to 9. So if we want f of 9, that's the output. What is the output? The y value that goes with 9. So if you're looking at our series of ordered pairs, find the ordered pair that has an x value of 9 and type in the chat box what the y value is. Okay, I've got 2 people saying 7. So you look for your input that has an x of 9, and then what it matches with, that is our function value, our output. So f of 9 is equal to 7. So it's just another way of asking, making sure you know how to read an ordered pair, essentially. Now the second one says, for what value of x is f of x equals 6? So they're giving us the y value in this case, because f of x is equal to y. So if you've got f of x equals 6, that's telling us that y is equal to 6. So if you look at your set of ordered pairs, what x value has a y value of 6? So go ahead and type that in the chart or into the chat. -1. Yep. So we found a y of 6, which means the x value is -1. And so that's the answer here. For what value of x is f of x equals 6? That is -1. So they're asking you to read these ordered pairs, but it's worded differently. In this case, they gave us the y, and we're looking for the x. In the other case, you're given the x, and you're looking for the y. Are there any questions? Okay, so last one, I wanted to finish off with a word problem so you can kind of see how function notation is used in real life with word problems, that sort of thing, because that's usually where they're used. Functions are used a lot with word problems to give some context. So at a restaurant, if a party has 8 or more people, the gratuity is automatically added to the bill. If X is the cost of the meal, then the total bill C of X, so that's telling us our output is the total cost, that's why I used C. So X is our input cost, big C is the output cost, C of X, then the total bill C of X with an 18% gratuity and a 6% sales tax is given by this equation. So we have C of X equals X, so that's the cost of the bill, plus 0.06X, so we've added on the 6% sales tax by that part, 6% of the bill, and then 0.18X, that's the 18% gratuity. So you can see how each part is added onto the bill to give us our total bill. So the first part says evaluate C of 225. So I want you guys to try to do this C of 225 on your own. You know, do it on your paper or whatever. Figure out what is going to be the answer to C of 225. And I'm not going to write anything down for a little bit because I want you guys to try it first. And then when you get an answer, feel free to type it in the chat if you feel comfortable. But I'm not going to write anything for a while because I want you guys to try this first. Okay, I've got one answer. See if anybody else comes up with something. I'll start writing some stuff. So Josh, now we got a second person. Okay, you guys both got 279. So, you know, let's go through the problem, see if you're right, see if there's consensus. So you're replacing X with 225, and then we're following the order of operations on the right. So I've got 225, then I need to do 0.06 plus 225, which gives me 225.06. And then 0.18 times 225. Wait, let me double check my calculator. I'm looking at it like, wait, 6% of 225 is not 225. I don't know what I typed in there, but I retyped it. That should give me 13.5. Much different answer. Always double check what you're putting in your calculator. Okay, 0.18 times 225, that's giving me 40.5. Now I add all of these up. We get 279. So I agree once I fixed my math there, my calculator error. double checked my math there. So the sales tax was $13.50. And then our gratuity was $40.50. So that's the amount for the tip. So we've got C of 225 equal to 279. So the second part here says, interpret the meaning of C of 225 in context of this problem. What this means, when you're told to interpret something, that means you're writing a sentence. So anywhere that you're told to interpret something and you're told to do it in context, you're writing a sentence telling us what these numbers mean. So in this case, we have to say, well, what is our 225? That's the input, that's the cost of the meal. So we would say for a meal cost of, and you want to include your units, $225, because that's our input. And you have to have it in context. So context means it's relating to the problem, which is, you know, cost of the meal. So you have to actually use the words that are in the problem here. The total bill, that's the output here, after, and it's good to be specific. So after gratuity and tax, you know, specifically saying that those are included here, is, and then our output was $279. So this is what it means to interpret in context. We have our value, C of 225 equals 279. Our input was 225. The output is 279. But to put this in context, you need to write a sentence that's relating to the problem. So we're telling us that the input of 225 was a meal cost, and then the output is the total bill after gratuity and tax, and that's 279. So you need to include enough information so that somebody knows what this means. I like to give an example of if you're on the job and, you know, if somebody asked you to solve a problem, if you gave them the answer C of 225 equals 279, they're going to be like, what are you talking about? But if you tell them, oh, for a meal cost of 225, the total bill after gratuity and tax is 279, they understand what you're talking about. So when you have word problems, we like to put our answers in words. We like to put it in context so that it actually makes sense to somebody, because that's all about communicating the math. It's fine to do the math and get your answers, but you want to be able to communicate that in a way that others can understand. And so that's why we're being asked to interpret the meaning, is how do you then communicate this answer? What does this answer actually mean? Are there any questions? Okay, I don't see any questions. Well, this was the last example that I had, so we're actually getting done a little bit early. I didn't have too much like I did the last time that I did this a couple weeks ago. So hopefully this makes sense with the function notation. The most important thing is do the stuff on the right. Don't really do anything on the left. You're doing things on the right side. If you can do that, you'll be fine. And, you know, we're going to start getting into the graphing and all that kind of stuff. Feel free to use a graphing calculator to make that easier for you. You know, that's completely fine. But from weeks 5, 6, 7, 8, basically the whole second half of the class, we're going to be doing stuff with function notation. So it's really important to understand what it means so that you can work with it as we get through the second half of the class. So, all right. Well, I will stop the recording.